Hey there, did you know our sun is actually a star? Yeah, it's the one that gives us light and heat, and this energy is, well, absolutely vital. Life on Earth, it really needs this energy. But where does all this energy come from? It's not just some normal fire. Nope, it's nuclear fusion. Stars, they're these giant balls of gas, and they shine brightly in the night sky. Our sun is just one of those stars, but there are many, many more out there. And guess what? All stars have a little secret. This secret, it's fusion. That's what makes them shine so brightly. Without it, well, we'd be left in darkness. Now, nuclear fusion, it's a natural process. It happens right in the cores of stars. And these cores, they're hot and dense with pressure that's just huge. These are like the perfect conditions for fusion. Think of it like a power plant that turns matter into energy, and then that energy flows out. So the sunlight on your face, that's fusion at work. The energy that plants use, yep, that's fusion too. It's a key cosmic process, and understanding it helps us learn about stars. Plus, it even hints at new energy possibilities for our future. It's like an idea borrowed from the stars. Alright, let's dive into how fusion works, shall we? Imagine these tiny atoms. Stars, they're mostly made of hydrogen, which is really light. In the core of a star, these atoms are zipping around, moving super fast, and they're squeezed together tightly. This is where the magic happens. Under all that heat and pressure, the atoms collide. But they don't just bounce off each other, they actually fuse, forming new atoms. This new atom? It's helium. And helium, well, it's heavier than hydrogen. Picture small blocks joining together to make a bigger block. That's the core idea of fusion. Now when these atoms fuse, something interesting happens. The new helium atom, it's lighter than the original parts. So where did the mass go? Einstein's famous equation, E equals mc squared, explains it. This lost mass, it turns into energy. And that energy is released as light and heat. This process, it happens over and over again. Billions of atoms fuse every single second, creating a constant flow of energy. This energy, it pushes out from the core and balances the pull of gravity. It's like a cosmic energy dance that keeps stars stable. So, humans, we've always been fascinated by the sun's power, right? We wondered, could we possibly copy it? Could we actually build a mini-sun? This idea, it really started to grow in the world of science. After World War II, we realized that fusion powered the sun and it held immense energy. That's when the dream of fusion power began. The 1950s, they were an exciting time. Scientists started experimenting, trying to replicate the sun's core. But this was no small task. The sun's core, it's millions of degrees hot and no material can contain it. So we needed some clever ideas, new ways to hold all that heat. Early tests, they used magnetic fields, which were like invisible bottles holding super hot gas. This gas, it's called plasma, and it's made up of atoms stripped bare. These magnetic bottles, they had names like tokamaks and stellarators. Scientists really hoped they would work, but those early efforts, they struggled. Plasma, it's very unstable and hard to control, like trying to hold jelly with magnets. It often escaped the fields, and reaching those high temperatures was tough. Keeping the plasma stable, even harder. Fusion, it's been a long and challenging road. The great fusion hurdles challenges we face. Why is fusion so hard? There are big challenges. First is temperature. We need 100 million degrees Celsius. This is hotter than the sun's core. Reaching this takes energy. Fusion must make more energy, more than we used to start. Second is confinement. How do you hold such heat? Material boxes would melt. So we use magnetic fields, they make a magnetic cage, but plasma is tricky stuff, it can leak out. Holding it long enough is key. Third is density. We need enough fuel particles. These particles must be close. This helps them collide and fuse. So we need dense plasma. Getting temperature, time, and density right. This is the Lawson criterion, a benchmark for success. Another challenge is fuel. Easiest fusion uses hydrogen types, deuterium and tritium. Deuterium is in seawater. Tritium is rare and radioactive. We must make tritium, perhaps from lithium. Managing tritium safely is vital. Neutrons also make materials radioactive. Modern marvels and future fire the path forward. Scientists are making progress, many projects show promise. One of the biggest is ITER. ITER is in France, many nations build it together. ITER aims for net energy More energy out than in. This is a giant step. Another way is inertial fusion. The NIF in the USA uses this. NIF has powerful lasers. Lasers blast a tiny fuel pellet. This crushes and heats fuel fast. Fuel should fuse before it scatters. NIF achieved ignition briefly. Fusion reactions sustain themselves. If we succeed, fusion is great. It could give clean energy. Fusion makes no greenhouse gases. Fuel is abundant. Deuterium is in oceans. Tritium can be made. This means endless energy. It could fight climate change. The road to fusion is long, but rewards are huge. Support fusion research. Learn about these projects. Follow ITER and NIF news. The dream of sun power on Earth. It is alive and growing. It could light our future.